In this last lecture in Unit 2 over metabolism, we're going to really focus on what happens to metabolism in exercise. I think this is one of the students' usually favorite lectures because a lot of this is somewhat relatable. We start to tie in all that idea of using glycolysis, using the Krebs cycle and electron transport chain, and how that's used to create energy, and then how that energy is then used to help us perform. In this lesson, we'll have several objectives throughout the chapter. First, the student is going to need to be able to determine which substrates and where that substrate came from is used during different exercise methods. We're going to talk about the idea of an oxygen deficit, and students need to know the mechanisms of how we pay that oxygen deficit back. Next, we're going to talk about lactate and lactate threshold and talk about what it means. And then the last thing is you'll need to know the ways that we measure energy expenditure and what they mean. So first we'll start out with metabolic substrates for rest and exercise. So the substrate utilization is going to be dependent heavily on both the intensity and duration of exercise. Indeed, this is going to be the main factor for picking whether we're utilizing more carbohydrates or more fats. Right. So if you remember from the previous lecture, we can use anaerobic processes. Anaerobic process defined as don't require oxygen for the creation of ATP. So some of these include free ATP stores, creatine phosphate, and using glucose going through glycolysis alone. You'll note that no proteins or lipids can be used in the anaerobic production of ATP. In aerobic, this is again requiring oxygen as the final electron acceptor in the electron transport chain for the production of ATP. It's great because it produces a lot of ATP, much more than anaerobic. However, the limitation is we have to have sufficient oxygen to keep it going. With aerobic, we're going to primarily use carbohydrates and triglycerides. Remember, both of them can feed in carbohydrates through glycolysis ending in pyruvate. Pyruvate converted into acetyl-CoA, which can be fed into the TCA cycle, and triglycerides, which can be broken into free fatty acids, and glycerol. Glycerol then can be converted to sugar similar to glucose and fed through glycolysis, and we can use those free fatty acids where we chop the fatty acid into 2 carbon segments, and then those are converted into acetyl-CoA. So one question that I pose here is, when are we not using aerobic metabolism? Right? So I want you to think about this before we start talking about the production and which exercises use them, because you're probably familiar with that aspect, but I think this is an interesting critical thinking question. The answer is, when are we not using aerobic metabolism is never, right? If you are not breathing and not using oxygen, then you are dead. Right? So at some point, at all points in time, we are using aerobic metabolism, even if it's just a tiny amount, right? We always have oxygen in the system, therefore aerobic systems are always generating. So I think this is an important concept, and I hope it doesn't confuse you, but I want you to think of this kind of as this continuum that, you know, even when we're never really relying only on anaerobic metabolism, right? At all points in time, pyruvate is getting turned into acetyl-CoA and shuttled into the mitochondrial for breakdown. Right? It just becomes, when does that become rate limiting, and when do we say, okay, we're not producing enough ATP from aerobic substrates, so we have to really boost our production, and the quickest and fastest way that we can do that is using these anaerobic pathways, which are much, much quicker than the aerobic pathways. Why is it quicker? Simply because of the number of steps, right? Free ATP, already there. Phosphocreatine, 1 step. Creatine kinase is all that's needed, 1 enzyme. Glycolysis is a 10-step process, so there's some steps in there, so that's why it's kind of the second or third fastest if you consider free ATP. And last but not least, we have aerobic, right? We have the entire Krebs cycle. We have all those pumpings of protons and electrons down the electron transport chain. It just takes a long time for that to gear up, and so you can imagine that's why. So let's take a look at the bioenergetic pathways for short-term, high-intensity exercise. Right? In general, when we say intense exercise, we mean this is all up for as long as you can go, and we'll talk about this as we move forward, but we'll highlight really early on. So early on in high-intense, short-duration exercise, ATP comes predominantly from our anaerobic pathways. Again, it's the fastest way to produce ATP, right? And we can break that down even further, that within the first few seconds, so about 1 to 5 seconds, we use the phosphocreatine system primarily to generate ATP. As that duration extends from about 5 to 45 seconds, we're using both phosphocreatine system, and glycolysis becomes much more predominant, and then above 45 seconds, a combination of anaerobic and aerobic. I'll make another point here that I'll reiterate a lot during lab is, at all points in time, all three systems are going to be active during exercise. So even at really high intense exercise, we're going to have some oxygen available, making ATP. Even in the longest duration, slowest moving parts, we still have the phosphocreatine system that can contribute. Even if it's tiny, tiny amounts, they're all three going to contribute to ATP production. So I think this figure really shows this as we kind of look at the events, so percent aerobic and percent anaerobic metabolism, right? So from 1 to 3 seconds or 5 seconds according to your book, we rely almost exclusively on anaerobic. I hate this, right? So this is about 99% anaerobic, 1% aerobic. Right? I just told you, we're using all three systems all at once. Right? So go ahead, cross that out in this figure and know that it's 1% here, tiny amount of aerobic. We still have oxygen available. We're still feeding the electron transport chain and moving it. We just can't generate it fast enough. As the duration of the exercise increases, again here to 10 seconds, you'll see the percent of anaerobic metabolism goes down, and then therefore we're picking that up by aerobic. And here on the other side is kind of putting in some of the some different exercises or activities or competitions that are using these. So for example, doing a 1 rep max or a power lifting here, doing a diving, which is going to take a very short amount of time. Football here, each play lasts about 4 to 6 seconds for most of them. Maybe a little longer if you're running a deep pass play or something, but most of them are pretty short, less than 10 seconds. And then as we start to creep up, again, we can have 30 seconds. And again, the percent of anaerobic is going to decrease to where at roughly around 2 minutes, we start to see it's about a 50-50 split. Okay. So about exercise intensity, about 2 minutes, about 50-50 anaerobic and aerobic is when they start to really take over. And then beyond 2 minutes, aerobic is our predominant source of ATP production. And again, I'm going to make one more correction here. This is 99% here and 1% here, or maybe even less. But maybe tiny, but it's still taking place. And again, these are really long events. So again, just to kind of summarize, there's a gradual shift from one energy system to the next. Anaerobic at the beginning, aerobic during longer duration exercises. So this is good for knowing, which system you need to train. So if you're in one of these, you need to really focus on anaerobic systems, where if you're doing something like a marathon or 2-mile run or even a 1-mile run, you need to work on aerobic systems. Okay, so let's look at then how we utilize these anaerobic systems going from rest to exercise. So what happens at the beginning of exercise? So the first part that I'll make here is that one of the core concepts of exercise physiology is that our metabolic supply always equals our metabolic demand. In other words, when we are going to try to go out and run, we have the ability to generate the amount of ATP for the speed that we are trying to run, right? And that's illustrated by these two figures here. So for example, you get on the treadmill and the treadmill's running 7 miles an hour. This is a pretty brisk jog here, for those of you who aren't familiar with what 7 miles per hour feels like. And if we look at figure B, the amount of ATP required to run 7 miles is the amount of ATP, 7 miles per hour is the amount of ATP that we are able to generate. So we go from this low level instantly to the amount of ATP required to run 7 miles per hour. And again, most of you guys can think that, right? So if you wanted to go from a standstill to a sprint, yeah, it takes a few strides or whatever to get going. But if you've watched the 100-meter dash, or you've seen that they get up to full speed really quickly, right? There is no this like lag and delay, no waiting for metabolism to catch up. We're able to generate that amount of ATP to make that movement really fast and do it. So for this, we reach this metabolic supply and demand really quickly. But what we really talk about is during lower intensity exercises, so submaximal exercises, we are able to meet most of our demand. This would be for an exercise that's more than 30 seconds long, and in general, more than 2 minutes long. So if you'll go back, anything over 2 minutes is going to be 50-50 or more on the aerobic side. Right, so here we're talking about time in a couple minutes. Again, as you start to run, this purple line says the amount of ATP we're producing, whereas here is the amount of oxygen we're consuming. If you remember from the last lecture, when I say oxygen being consumed, I mean that's being the final electron acceptor in the electron transport chain and is ultimately disappearing, and we can measure that, and we'll discuss how that is at the end of this lecture. Also, if you're in lab, you're not only hearing about this, but actually seeing and being part of the measurement as a subject and having your own VO2 measured. Right. So again, we're able to meet our ATP requirement. However, you'll see that the oxygen consumption here in this green line, which is directly related to the amount of ATP created from aerobic metabolism. That's what we're measuring here. So we can just write aerobic ATP production. On this side. Okay. So if we look at the amount of ATP produced, you'll notice that it takes us a little while in order for our ATP to become ATP demand to be met by oxygen. In fact, when we do this, we call this steady state oxygen consumption, and usually lasts about 2 to 3 minutes. Right? So how then are we filling in this ATP gap? Right? We're not making enough aerobically. So of course, if we're not making enough aerobically, this is then coming from anaerobic metabolism. So that fills in that gap early on so that we can maintain the requirement for whatever the exercise that we are doing. So let's take a look at this again by percentages of aerobic and anaerobic energy contributions by race speed, and kind of show early on that as the time of that exercise, or in this case competition, lasts, that we see the shift. So it's looking at kind of the start every 10 seconds or so. They'll say, what's the contribution, right? So early on, the first race that they talk about is the 200-meter race. So this is going to take anywhere from 20 to 30 seconds, depending on the speed. So, Michael Johnson ran it in, 19 or so seconds. Most people aren't running it that fast, but 20 to 30 seconds here. So what's happening again at the very beginning? We're meeting so much of that demand by anaerobic metabolism. It's the quickest, fastest way to generate a lot of ATP. Right? 200 meters or all-out sprint at the beginning. We meet that by using mostly anaerobic because it's fast. Minimal steps to create ATP. And then as you can see, we already start to begin the transition here. So that at 20 seconds, again, aerobic metabolism is taking up about 30% of the ATP production load, and anaerobic is falling, but still you would consider this a very anaerobic sport, right? It is still the predominant during the race. If we then move to the 400 meters, this is a really beautiful curve. Again, starts out in a near full sprint. These guys are moving really quickly, especially if you're talking about Olympic caliber runners. Anaerobic, providing a huge amount of ATP production here 10 seconds into the race, and you'll see the slope as it slowly falls, and ATP from aerobic slowly increases. Right? Following exactly that pattern of earlier, but because we're not out to that 2 or 3 minutes, right? Our aerobic isn't able to fully meet that demand, and so we are requiring the anaerobic systems. You'll see here that our steady state in the 800 meters is actually met. So an 800 meter usually lasts, give or take, about 2 minutes. Faster if it's Olympic sprinters, but we'll say this is about a 2-minute exercise. One thing that you'll note, again, that same pattern, aerobic really fast in that rest to transition, and then it slowly falls, whereas aerobic metabolism slowly starts to catch up, and we're able to essentially increase the rate of production from aerobic metabolism and reach steady state usually a couple minutes in. And the 1500, I'll make this point also. The 800 meters, since this is still a pretty good sprint, we're still requiring lots of ATP, and so you'll see that there is still a pretty decent anaerobic amount of energy produced during this race. In the 1500 meters, again, this is a mostly aerobic, so early on you'll see 10 seconds anaerobic, and then it slowly falls. And again, all of these figures highlight the idea that we're using all systems, both aerobic and anaerobic, at the same time. So why can't we use aerobic immediately, right? So why can't, if I wanted to just start out to run, aerobic is producing the most ATP, right? We're getting a net of 32 ATP using glucose through that, or using fats, right? That's 16 carbon. We were getting a net of 98 in a 12 carbon molecule from the last lecture, right? So that's way better than the net 2 that we get from glycolysis. So of course it would make sense if we wanted to get the most ATP. Why don't we do that? But why do we need these anaerobic systems early on? So there's a couple of reasons why. The first is the idea that there's an adequate oxygen supply to muscles at the onset of exercise, right? It takes us a little bit of time to get blood flow to increase, right? So if mitochondria don't have enough oxygen, note I didn't say they don't have any, I just say they don't have enough, right? So pyruvate is trying to get into the cell. It would love to go through the Krebs cycle, love to produce NADH, FADH, shuttle those to the electron transport chain, and have oxygen act as the final electron acceptor. However, if we don't have this abundance of oxygen, that process comes to a slower rate than what we need, right? And our mitochondria are kind of like waiting on us, and our brain is trying to adjust the cardiovascular system to get blood flow, which is carrying oxygen to it as quickly as possible. Those adaptations will be talked about in the next unit, Unit 3, cardiovascular system and the adaptations to exercise. Right? So therefore, this is restricting aerobic ATP, and even may be true at very high intensity exercise. The second is the idea that there may be a delay in the stimuli to fully activate oxidative phosphorylation. This is the idea of inertia of metabolism, and is very, very true. So When we talked in the last module, I mentioned one of the things that you need to think about and know during the idea of the Krebs cycle is that these enzymes, there's certain ones that are controllable. And the same for phosphofructokinase. It's a rate-limiting enzyme because we can control it to increase the rate, right? So how do we actually control and increase the rate? Well, this is actually a feed-forward mechanism. This is a positive feedback mechanism, right? So what happens is the products that are produced during exercise, right? So in exercise, we are churning a lot of ATP in that cross-bridge cycling that we talked about in the first unit. We're just churning ATP, using it like crazy, making ADP. In your discussion, you guys are looking for how we can then convert when ADP is used to make AMP, and you'll see the reason that I have that is because AMP is actually one of the most predominant stimulators of metabolism. So as we start to ramp up our muscle contractions, start to produce ADP and AMP, what we're going to do is we're going to cause a positive feedback system on these enzymes. So ADP will stimulate faster actions of creatine kinase, faster reactions of phosphofructose kinase, and faster action of isocitrate dehydrogenase, which is the rate-limiting enzyme in the Krebs cycle, and it will also work on cytochrome C. So AMP and ADP are both very potent stimulators. Another one is calcium, right? And you go, why is calcium such a potent stimulator of the Krebs cycle? That's because calcium is being released by the SR and binding true to troponin C, right? It's in the muscle cell, in and around mitochondria, and so the mitochondria then sense that as if there's calcium flux coming out and being inside the cell, the mitochondria sense that, knowing that the muscles are contracting, and therefore they start to ramp up aerobic metabolism. We also have a change in pH, which I think is good. So an increase in pH will increase glycolysis as well, and we'll see that a little bit later. Right. So then, what are some inhibitors? What kind of molecules do you think would say, okay, slow down, slow down? One would, of course, be the obvious, is if we have ATP, if we have lots and lots of ATP, we don't need these systems kind of running at full force, right? So that's one. A decrease in pH. If we have an excess of NADH, you remember that this will essentially stop the Krebs cycle. Why is this stopping the Krebs cycle? Because NADH isn't available to be created. If we have too much NADH, we can't oxidize NAD into NADH, and so it will just stop the entire cycle. That way we aren't feeding pyruvate into it and wasting that molecule. Okay. So again, the idea of inertia of metabolism. So as we start to metabolize, as we start to break these down, we get these powerful stimuli, which then are a positive feedback and ramp the system up and get it going and make it go faster and faster and faster. And that way, as that takes a couple minutes to get to maximal rate, and we can then reach maximal exercise or maximal aerobic metabolism to meet demand. All right, so that'll end it for this lecture. Next, we're going to come in and talk about actually the oxygen deficit and debt that are paid during exercise at the beginning and at the end of exercise, since we just finished up what happens within exercise.